This is the second video in the module Models in R. And as you'll recall, in the previous video, we looked at our sample data, shown in the scatter plot here, and then hypothesized a model to try to explain the relationship between the two variables x and y. And the model we're using, the model family, is the standard straight lines using the slope-intercept formula. And that model family is characterized by the two parameters W1 and W2. And so we can create a model, or what we call the model instance, by just assigning values to that W1 and W2. And where we left off in the previous video is we had developed 200 random models by generating random variates for W1 and W2. So we have that here in our R script, and in this case we have plotted all of those models. There's the generation code for our 200, and we've plotted all 200 of those models. And what we want to do in this video is look at a process for identifying good models. So we have defined the model and defined the model family, and now we want to look at how do we find a good model. And so if we go back to our OneNote, what we want to do is we want to define a metric to define or to describe the quality of the fit. And so what we're particularly interested in is this distance, standard regression. If we look at this point right here, this is some xi, yi, and this point would be xi, yi hat, the predicted value. And so we're interested in this difference here. And we're going to look at two different metrics of that. Let me see if I can find some room here. We're going to look at what's called the root mean square, or RMS, which is simply the average 1 over n summation of the different squared. So y I minus yi hat squared, square root of that value, so the root mean squared. And the second standard value that we'll look at is the residual sum of squares. Residual sum of squares is simply the yi minus yi hat quantity squared. And so in the textbook, this is the model that they use in the textbook for the example that they do, and so we will start out with that. So if we go back to our script here, the first thing we want to do is we want to actually implement those values. So I want to have a way so that I can systematically, given a model and given the data, compute the value of the distance. In this case, either the root mean squared or the residual sum of squares. And so what we're going to do is a systematic way that is generally applicable to a wide variety of model families. So here's what we're going to do. First thing we're going to do is we are going to define a function that takes the model parameters and a set of x values and then returns the corresponding y values. So I want to look at that in a little bit more detail. So I've extracted it out here, and we can zoom in on that. Let me just change my pen color here. Get my red pen back, and so you can see I just copied this over. And so what we have is two parameters. One is our model, and our model is characterized by a vector, which we will have the two terms W1 and W2, so they come in as a vector. And our data is a data frame, and it contains at least x values. So it contains at least a set of x values. It might contain more variables, so we could send our standard data or our sample data frame in. So it's okay if it has other values, but it needs to have the x values. And what the function does is it uses the vector computation to compute our model value, which again was simply W1 plus W2 x. And so it implements that in vector fashion and returns the corresponding vector. And so if we invoke that, so let me define our model here. So it's control enter, and then a sample model invocation. And so when we invoke that, you can see that what was returned was a vector of 25 points. And so these 25 points are the distances. So the individual distances from the points to the corresponding, I'm sorry, what that's returned is the y values, not the differences, the y values. So let me back up and make sure that's clear. What the function does is it generates the y values for a given model, W1 and W2, and the corresponding x values. So what I return are the y values corresponding to the x values in our sample data. So if we had looked at this plot, if we go back to our original plot, let's go back to our plot here, right here, which is actually what we did. What we're actually being returned are these individual y values. So this y value, this y value, this y value, and so on. That's what's being returned there. Sorry about that confusion. And now that we have those y values, we can create another function. We have a function that generates those y values, I should say. We're going to create another function that computes the distance. And so here is that function right here. And as we did before, I'm going to jump over into OneNote and talk a little bit about this function. And so what we're doing is we've defined a function called measure distance, and it takes the same two parameters, the model, which is a vector W1, W2, and the data frame that contains at least the x components, because we're going to use that function call that we just created for model 1. And so we can compute our metric by computing the difference. So diff is equal to the observed value minus the model value. So again, this is going to do the vectorized version, and so diff will end up being a vector where each value corresponds to the difference between the actual value from that the actual y value from that corresponding x and the generated y value generated from our model w at that same point. And so what I'm doing here, the one I haven't uncommented is root mean squared. So we're just going to square the vector, take the mean of that, and then take the square root. And so this is the value, this is the return value from the function. So if we go back to our code, we can see that we have, there's my measure distance, and let's just do an invocation of that. So I'm going to create it, and then I'm going to make a call. And so this value, 117218.6, is the root mean squared difference between our observed values and our hypothesized values for the given data set and the given model. Okay, so now I have a method to compute the distance for a given model and our data set. And let's go back to and look at our what we really want to do. So now that I have a way to measure the distance, what I'd like to do is be able to just add a distance column here so that I compute distance 1, distance 2, distance m for each one of our models. And if I do that, once I compute all these distances, I can then pick the minimum distance or a set of minimum distances. And so we're back to our original problem of identifying good solution from our data set or the best solution. We're simply going to compute the distance associated with each one and then select either the minimum value or some subset of the minimum values from our existing set. So one way that I could do this is I could just do a loop. So I could program a loop that just goes through our entire data set and then calls this function measure distance and then systematically passes W1, W2 data, W1, W2 2 data, 3 data, so on in a loop fashion. Of course, that's not really the standard way of doing things in R. So let's look at a more general way or a simpler way to do that. And in order to do that, what we're going to do is we're going to use the module per to help us out. But I need to make one more little change before I can do that. I need a 2-parameter function for the per code. So let's go back and look. So what I need to be able to do is have a function where I only send these 2 parameters. And when you look at our distance, we have the 2 parameters and the data. So what I'm going to do is define a helper function called simdist1, where the only purpose of this function is to extract our 2-point. So notice I'm not sending these in vector form now. I'm just sending W1 and W2. And then inside the function, I'm creating the W1, W2 vector, and then I'm sending my default data set. In other words, the sample that I have. And so what I can do with sim_dist1 is I can call it with the 2 parameters, and then it will return to me the computed distance from the default data set. So now that I have that, so let me go ahead and define that right here, Control Enter. Now I can invoke it, so if I invoke it once here, if I just call sim_dist1, you can see that it generated the same value. So above where I did the measure distance, of course I had to send it a vector and the data frame, and now I simply send the 2 parameters. And so I can use that with per. We're not going to get into the details of how per works, but you can see what's going on here is that I'm using a function called map2double, where it's saying take the 2 parameters, W1 and W2, in the data frame, and the function sim_dist1, and it's going to systematically apply this in vector form. And since I'm using mutate, I'm going to create a new column called dist, which will correspond to the distances. So when we run that, if we run that here, let's run that, and then I can go back and look. When I go back to my models, now you can see that we in fact have the distance value associated with each model. So now I have my 200 models, and with that single function call, I've sampled or computed the distance from each one of the models. Okay, so let's plot the top 10 best models. Again, what this code does, this is from the book, it says, okay, give me the top 10 models. And really what we're going to do is we're just going to filter our models using the rank dist less than or equal to 10. So the rank function will rank the values, and then we're going to pick the top 10 values, and we're going to use those to plot lines. So we do that, and then run that. There we go. And you can see we've taken our previous plot and we've improved it significantly, whereas before when we plotted all 200 we had lines going all over the place because how we randomly generated the values. But now that we've computed the distance, we've filtered it out into the top 10. And these, relative to what we saw earlier, these are all 10 pretty good looking fits. So our objective was to find the best value. So recall back from the beginning, let me scroll back here. Our objective on this module, this video, was to take our 200 and find the best one. Well, we've done that. We've actually picked off the top 10, but I could just as easily go in and pick the top and print the top model. If you want to do that, if I want to stop the process here, I could just pick the rank 1 model, and that would be the best from our data set. And what we're going to do in the next video, so this is the end of this video, and in the next video we're going to carry on this procedure to try to do some more systematic improvement of this solution.